So far in this chapter, I have spoken about coordinates, okay? So coordinates are a way in which I provide you with a set of 3 numbers and you can tell what position I'm talking about. So for example, I give you the 3 numbers x, y, z, and then you know I'm referring to a certain position. But I can also give you 3 numbers, rho, phi, z, that is in cylindrical coordinates, and you still know what position I'm talking about, right? So for example, here, which is cylindrical coordinates, we have 3 sliders corresponding to each of those 3 numbers. Yeah, each slider is associated with a certain number. So now I can change the number, and this means that I'm referring to a different position in space. Okay? So coordinates are used to describe positions in space. Coordinates are a set of numbers used to describe positions in space. But there is another thing. So what if I want to describe not a certain position or location in space, but I want to describe a vector at that position? Okay? So let me try to clarify this. Imagine I am in 2 dimensions, x, y. So I can describe this location, for example, using my x and y coordinates, or using my rho and phi polar coordinates. Yeah. So using those 2 numbers, I specify this position. But now maybe I'm trying to describe some vector field. For example, I'm trying to describe the electric field that exists at this position. So the electric field is a vector, and it might be pointing this way, or it might be pointing this way, or it might be pointing any other way in space, yeah? So the direction of the electric field in principle has nothing to do with the coordinates x, y, or rho, phi, yeah? So how do we describe this vector? Well, as you know, to describe a vector, we need some basis, yeah? So we need to choose a basis. So normally, you just say that the vector is vx in the x-hat direction plus vy in the y-hat direction. But it turns out that the same way that we can describe positions using numbers that are not xy, like rho phi in polar coordinates, we can also choose unit vectors that are not x-hat and y-hat, okay? And that is the concept of unit vectors in polar or cylindrical or spherical coordinates, okay? So here is a simple to understand example. These are unit vectors for polar coordinates in 2 dimensions. So when we are in rectangular, we are here on the left. So we can describe positions using the rectangular coordinates, x and y. Notice that x and y here are written not in bold, because they are not vectors, they are like a scalar, yeah? X and y, it's simply 2 numbers indicating the position. But we can also have the rectangular basis, x hat and y hat. This time this is a bold notation because this is a vector, yeah? And it represents these 2 arrows, x hat and y hat. And that is rectangular basis. So any vector can be described using this basis. For example, this vector here would be equal to 2x hat plus 1 y hat. Yeah, that will be the vector v there. Now, we can also use what we call unit vectors in polar coordinates. And these unit vectors are usually, the way I do it is I use the letter E with a subscript and the associated coordinate. So E rho, E hat rho, is a unit vector that points in the direction in which rho increases, okay? And E phi hat is a unit vector that points in the direction in which phi increases, okay? So if we now moved the slider for phi, so if this angle, we now increased it, our location would move in this direction, right? So it would go around a circle like this, yeah? And therefore this vector, E phi hat, is pointing in this direction. But the key difficulty with unit vectors in polar coordinates is that they depend on where you are. So if instead of being here, we were here, we were using this phi here, then our 2 unit vectors would be E rho pointing in the direction of rho. This would be E hat rho. And E phi hat would be pointing in this direction. Okay? So these are polar unit vectors, the polar unit vectors, and they depend on our position. Okay? So that's why you can write the polar unit vectors in terms of x hat and y hat, but they depend on our position. In fact, they depend on phi, on the coordinate phi, the azimuthal angle. Okay? Good. The expressions for the unit vectors in different coordinate systems, they are given in the list of useful equations. So you can see I provide you with this table here. So you already saw the coordinates in the previous videos, but I also provide you with the unit vectors in those coordinates. Okay? So the polar unit vectors would be E rho and E phi, these two vectors here. Okay? Okay, and what about cylindrical and spherical unit vectors? Well, we also have those, of course. And the best way to understand them is to come to my applet here of cylindrical coordinates. So right now I'm showing the three numbers, which are the three coordinates in cylindrical coordinates. But now I'm going to add the basis vectors. So for this I have this tick here, show basis. Now we are seeing three unit vectors, which are E rho hat, E z hat, and E phi hat. And notice how when we change our coordinates, so when we change the position we are describing, the vectors rotate. Okay, so these basis vectors are not fixed like x hat and y hat, which are always the same. These three vectors depend on where you are. Okay, so E rho hat points in the direction in which you would move the position if you increased rho. So if you increase rho, you are moving away from the z-axis. So that's the direction in which E rho hat points. E z hat points in the direction in which you move if you increase z. So if you increase z, you move up. That's why E z hat is pointing up. And E phi hat is pointing in the direction in which you move when you increase phi. So if you increase phi, you are moving around in a circle, yeah, around this cylinder. So this E phi hat is a unit vector tangent to this circle. Okay? So these are the unit vectors in cylindrical coordinates. Okay? And they are given by their own equations, which are here. So notice that this would be for polar coordinates, for cylindrical. Notice that the equations for cylindrical coordinates are the same as those for polar. So these two equations are the same as these two. We just have to add the fact that E z hat is actually z hat, the same basis vector as in rectangular coordinates, okay? Because you know that z is the same whether you are in rectangular or in cylindrical coordinates. Now, what about spherical coordinates? Well, now things get a bit uglier, as you can see here, but you shouldn't be scared by this. Firstly, because I give you the equations in the table, so you have them here. For spherical coordinates, you have the unit vectors, yeah? So you shouldn't be scared about trying to remember this. And secondly, because the concept is simple. If I change the applet now we are in spherical coordinates. So now remember, we have r, phi, and theta. We have two angles and the distance to the origin, yeah? And remember, we can change r, we can change theta, and so on. But these are the coordinates. What about the unit vectors in this basis? So I can click here, show basis. And now you can see three unit vectors. So these three unit vectors are pointing in the direction in which the position moves when you change each of the three coordinates. So let's walk through them. For example, it's a bit tricky to see. We need to change our point of view. So ER is pointing in the radial direction, away from the origin. And that's because when we increase the coordinate r, we are moving in that direction. So that's why ER hat is pointing in that direction, okay? Now, E phi hat is pointing in the direction tangent. So if we look at this from above, we look at it from above. So you notice that by changing our azimuthal angle phi, we are moving around in a circle. So this vector is always pointing tangent to that circle, because that's the direction in which we move when we increase our coordinate phi. Yeah. And then finally, maybe the one that is less intuitive is E theta hat. So E theta hat is pointing in the direction in which we move when you increase theta. So when you increase theta, you are moving along the surface of a sphere. Actually, it might be easier to picture if I add the sphere here. Yeah. So now I'm decreasing theta, the angle with the z-axis, and I'm moving up the sphere. And if I increase theta, I'm moving down this sphere. Yeah. So this E theta hat vector is always tangent to the sphere. You can see it's tangent to the sphere, and it's always pointing downwards in the direction in which we increase the angle theta. Okay? So therefore, the vectors ER hat, E theta hat, and E phi hat, then they depend on the two angles theta and phi. And that's what you can indeed see in the equations for the unit vectors. So you can see that ER hat, E theta hat, and E phi hat, they indeed depend on the angles theta and phi, on both angles. Okay? So I hope that makes sense. So what does this mean? The fact that we have now new unit vectors, it means that, let me remove what I drew here and go back to the simple case. So remember, here we had a vector v, which we wrote as 2x hat plus 1y hat. But this same vector v, which is this vector here, this same vector v, we can write it in terms of E rho hat and E phi hat. Okay, I don't know the numbers here, but we can move in the direction of E rho up to here. So this looks like 2 point something, let's say 2.3 E rho hat. I'm making up the numbers, yeah, but this seems like this would be 1, this would be 2, and then 0.3 to arrive here. And then we need to move in the downward direction. We need to move in this direction here. So that direction is minus E phi hat. So, and it's not even 1, it's less than a half, right? It's less than half this distance, what we need to move down. So this might be something like minus 0.3 E phi hat, for example, yeah? So then this vector v would be equal to 2.3 E rho hat minus 0.3 E phi hat. And this would describe some sort of vector v that I drew here. Okay, you understand? So of course, remember that E rho hat and E phi hat depends on rho and phi, right? Because if we were in another position here, then E phi hat would be different and E rho hat would be different. So then this vector v would be described using different coefficients. So this means that the coefficients for the vector depend on where we are. And that's I would say that is the disadvantage of using unit vectors in coordinates that are not rectangular coordinates. But the advantage is that there are many fields. For example, the gravitational field always points towards the planet. That we could say we have a planet at the origin. And therefore the gravitational field is a vector, and we can just describe it in the direction of minus E rho hat. Yeah, and that's it, because it's the direction of this field. So it makes sense in some physical situations to use these bases, the polar basis, the cylindrical basis, and the spherical basis. And in the next videos, I'm going to show you examples of using these bases to describe vector fields. Okay? So thanks for watching, and see you in the next video.